Hi everyone. Today we're not talking about flow matching anymore. We're talking about action matching, and rather very exciting direction. And one of my favorite papers at ICML this year, actually. So let's go.
So my name is Kirill Neklyudov, and yeah, today I'm gonna tell you about action matching. That's our paper that we presented at ICML together with Rob, Daniel, and Ali. And yeah, that's like a little presentation. And I want to start with a slide. I was trying to capture the idea of action matching in one slide, and I decided that yeah, it's something like this. So we observe some samples from some distribution in time, uncorrelated samples. That's important. But essentially, we want to recover the underlying process. So there is like some stochastic process we can sample from it, and we collect the data, and we want to recover what's the process guiding this change of the distribution. And you here you can clearly see that there are these uncorrelated samples. They drift slowly from left to right. So it's a very simple process. We can see what happens, right? And maybe I should give some motivation. So I think one of the main motivations is called trajectory inference of population, and it's an active area of research in biology. For the following reason, because you can think that you have like a population of cells, like a distribution of cells. Every sample is, let's say it's a latent representation of a cell, because, okay, we do like, the actual representation is discrete, but then let's say we map it to some latent space because we want to operate in continuous space. The problem is, in nature, once we measure the cell, we destroy it. So to get this observation, we destroy the cell, so we cannot track the trajectory of this single cell, like what happens to it through its evolution. So once we get the cell, we measure it, we destroy it, and that's why the samples are uncorrelated. That like at time like 1 second and at time 2 seconds, the samples are completely independent. So another application that you might guess already from this kind of measurement that kills the system is like quantum mechanics. Let's say we observe some quantum phenomena, and we can stop at some point, we can measure it, we get a measurement of this quantum system in total. So once again, the problem is that once we collapse the wave function, we cannot uncollapse it, let it go for 1 more second and measure it again. So measuring kind of trajectory, there are no these trajectories actually, but what you can do is that you can repeat the process multiple times. So you propagate your system for half a second. Every time you collapse it, you measure it, and you get these independent samples. Another example is for social sciences. Probably you can think that you poll some people, you get their answers on some questionnaire, and one for obvious privacy reasons, you cannot track a single person in time, right? That would be insane. Instead, you just you sample independent populations, but you still want to kind of get the idea where does it go, how does it change. So that's why you want to build this model. And the data will look something like this here, with color. I plot the time. So we have these different snapshots, and let's say they're dense in time. Let's not go to this question. Let's say we can, at any time, we can pause the system and sample from it, and this is our data, a lot of samples from different time steps. So what's the underlying process? And that's kind of the main question of the paper, like how do we approach it? And this brings us to like a more like to the first point on our list. This is like problem statements. From the evolution of a distribution, we want to find the underlying vector field. And I already used the word vector field, so let me tell you like a bit about the continuity equation and what do we formally mean by saying what's the underlying process, right? So let's say we have this vector field, and you can see integral curves here of this vector field v of x, and you have some initial samples from some distribution, and every sample goes down this integral curve, right? So we integrate the ODE with the corresponding vector field, and we can run these samples, and we can clearly see that the density of samples changes in time, right? So we can see it like with the naked eye. The continuity equation is a very fundamental thing, but it's very simple. It tells us how the density changes for the corresponding vector field. So here qt is the density that depends on time t. V of x is the vector field, so it's like an arrow at every point x sticking out of it, right? And this is the divergence operator, which is the sum of derivatives. And the continuity equation basically tells us, okay, if you tell me the density and the vector field, I'll tell you how the density changes. And that's what I want you to think about the continuity equation, because now we can kind of reverse the question. We can say, okay, I observe some change of density, let's say like this like drift of a Gaussian to the right. And I want to ask the question, I want to go to the continuity equation and kind of reverse it. I want to ask the question, I know the change of density. Can I get the vector field by any chance? And just to get some intuition, let's look what's like of different examples. What might really happen? What, for example, we can think that like there are like underlying samples, right? And they all drift to the right, but they also rotate around the center of this Gaussian on their way, right? Another option might be like some stochastic process where like samples, they kind of like they just like they run around with these like a Brownian motion, also drifting to the right, but like preserving distribution. And so there are like different examples of what might happen kind of like on the state space to the samples, right? And the answer is kind of like negative, right? So given the change of density, we cannot really say what's the vector field. But to make it like to get some answer, we can narrow down, we can be more precise, and we can say, okay, let's choose the vector field that does minimal job in a sense, right? So for example, for this Gaussian, we want to choose the vector field that just does the drift, but doesn't have this kind of like rotating component, right, of samples. That's why it's kind of minimal. And to put it in the language of mathematics, we can write this. So let's start from the right. So we say that like, okay, let's consider all the vector fields that satisfy the continuity equation, and this is our like strict requirement. We have to do this, right? And among these vector fields, we want to choose the vector field that has like minimal kinetic energy. And this is like kinetic energy because that's literally just like squared norm of the vector field, 1/2. So this is literally like kinetic energy of samples. And we can just write this problem with the Lagrange multiplier as like constraint optimization problem. And we can take the derivative with respect to v, because v is the unknown in this problem, right? So the derivative will be functional, but like that's all right. It's pretty much the same as usual derivative, and we'll get this. So the derivative equals to v minus nabla s, where s is the Lagrange multiplier once again. And at the optimum, obviously, we have to have this equation. So v minus nabla s equals 0. So we get that v equals to nabla s. And this is like one of the first thing we can learn from this problem, that like this vector field is a gradient flow. It's a gradient of some scalar function. By scalar function, I mean that like function s, it takes vector x from the state space and maps it to a scalar, right? Then we take the gradient of this function and we get a function that takes a vector from the state space and outputs a vector, because nabla s is a vector. And
Okay.
vector, yeah.
No, let's this point, then I ask.
Okay. So this vector field is unique. I'll just state it, not gonna prove it, maybe later during the discussion. But this vector field is unique. So which is kind of like expected, because the optimized objective is very nice. It's like it's a squared norm of a vector field. It's like convex, and like of course it's gonna be like a unique vector field, right? So maybe that's the right moment for the question, because I'm gonna go to the action matching.
Let's go 2 slides back and just have some repetition to make sure we get what's going on here, right? In your continuity equation up there on the top right, we have, what are we saying? We have our change of our density at the point x right now. Like how many samples do we have at this time, at this point right now? And then we have our vector field. And sort of if we now multiply our vector with the density at that point, and then we look at how much does this vector change, and then we again look at how much does this change, then this will tell us how much does the density change over time. And this is now like we only look at these continuous vector fields, but these are like basically all vector fields that we encounter in nature, right? Yeah, so it's not really a restriction. And then because you in this previous slide you showed we can have this rotating vector field having the same Q of t, or we can have the, I don't know, a crazy other curling around vector field. We instead don't say learn any of these, learn the one that does the least work, and maybe then we have the shortest path, so to say, if we follow that vector field. And now that's how we end up with this optimization problem. And then you do your Lagrangian thing, and we find out it needs to be, or the only, or this vector field is, this optimal vector field is the gradient of some scalar function, like of some function that just gives us a single number.
Yeah.
All right.
Yeah. So I would add that like the continuity equation, it puts some constraints, because you can't teleport mass, and we'll talk about mass teleportation a bit later, but it restricts the dynamic of the family of dynamics in some way. But as you've said, it's very natural thing. We continuity equation guides like many things in nature, and we can describe with it like pretty much all the processes in nature. Yeah. So we will discuss teleportation further. So so
may I also ask a question? So we are here talking about the continuity for a scalar function that basically is something like a score in a score matching model, right? So it's like a likelihood of the data.
You mean this one?
Yeah,
No,
the
it's
scalar
not.
function.
But it's not like this function S is not the likelihood of the data, and it's not a score. It's something different. So you should really think about it as action, because that's what's Hamilton-Jacobi formulation of classical mechanics tells you, that every every kind of like physical system, it follows the gradient of some action function.
Okay, I see. Yeah, my question was actually about basically preserving the conditions for proper distribution. So like in normalizing flows, we would have to deal with Jacobians, but here, because this is a scalar function,
that's a great question. So we will get to back to like a more like thorough discussion of this later, but now you should think about it in this picture. So if you have, so I don't need any restrictions on the vector field, because it's very kind of like straightforward in a way. I just throw like a bunch of samples at my plane, and then at every point of the plane I have a vector field that tells me where to go, and then I just like integrate ODEs for these samples. I just like rearrange my samples, right? And this corresponds to some distribution of samples, and that's it. And whatever vector field I choose, I can do this, and this will be a valid distribution. Does that make sense?
Yes. Thank you.
Okay. Yeah. Yeah, so we'll get back to it later. I think in the end we'll discuss like a bit of like geometric intuition.
Yeah, maybe like I think I said something like basically every vector field that we encounter in nature or in reality is follows a continuity equation, but I mean that's sort of just thinking about like fluid flows and so on. But if we think about these abstract things or your quantum stuff, then maybe this statement is completely wrong. So yeah, I think I have to take that back.
No. It's actually no. That's so you said that like it's very general, and this is actually true because you can write it. So the continuity equation is like a differential form of like some pretty much Gauss law, right? That like it tells you like how much density like flows in, the same amount like flows out, something like this, or like the density changes proportional to influx and outflux. And this is like a very you shouldn't think about continuity equation as describing some some natural phenomena, because you can find it in many natural phenomena, but you should think about it as like just like a mathematical tool that tells you about densities. But then you can apply to yes, indeed, like you can apply to some fluid flows, even like to quantum mechanics, because there is like a deterministic interpretation of quantum mechanics based on the continuity equation, and you can call it like Madelung transform or de Broglie-Bohm theory. And yeah, so it's I would say you're not wrong here. It's very fundamental. Let's go to the algorithm. Maybe it will elucidate something. So we figured out that like if the density changes somehow, there is a unique vector field, which we will denote as nabla S star. And once again, in our task, let's say like this is given somehow, like it's given through samples, but like so far we thought that like everything is given about it. It's just like abstract reasoning, right? So now let's try to find this nabla S star by minimizing this objective. The objective is very straightforward, just like L2 error, right? So this is, you can start thinking about S as the neural network, parameterizing this function. So it takes state vector and outputs a scalar. And we just want to minimize this function. If we are successful, then we'll clearly find S star, right?
And
So
right, this function is we integrate, or we integrate all of our samples. Okay, and we don't have samples over time, and then we look at each point in time, which is the actual gradient and what is the gradient that we get from our learned energy function. And yeah, then we hope that's the same at every point in time.
Mm-hmm.
Weighted by the density.
Yeah. So the problem, of course, with the minimization of these, like this straightforward minimization, is that like we don't know nabla S star, right? That's kind of our goal, to find it. So we just like open the brackets. We notice that the last term doesn't matter because the last term doesn't depend on S, and we want to like minimize with respect to S, right? So it's just constant. So the second term is the problem because the first term doesn't have nabla star and we can already estimate it. The second term is the problem. So, but we find these guys here kind of, and we do some integration by parts, and we'll arrive at this. So the objective on the left is equivalent in terms of optimization because we just dropped these constants, right? If we would write these constants, we would have the same. If we were to these constants, we would have the same. So this is equivalent to optimization of what's on the right. And what's on the right has like a nice property that's it depends only on samples because we can write it as just expectations. So we see that this is like expectations with respect to the distribution of samples of some function that depends on S, which we parameterize as like with a neural network, right? And we now can minimize this objective with respect to the parameters of the neural network.
Sorry, can I just to be very clear? We are trying to optimize here the star S star of T, right?
No.
This is our minimizer.
No. S star is sorry. Maybe so S star is the ground truth vector field that satisfies the
so it's vice versa.
So
I see.
We optimize with respect to S.
Okay. Then it makes sense. Okay, thank you.
Cool. So the algorithm looks very simple. So the one learning iteration of the algorithm is as follows. We just get a bunch of samples from time 0, from time 1. Then we sample time uniformly and get like intermediate samples, a bunch of intermediate samples where time is like uniformly distributed between 0 and 1. We plug these samples into this objective where we have these like boundary terms that correspond to batches collected at step 1 and 2. We have these intermediate terms that correspond to the batches batch collected at step 3. And now we can take the gradient, plug it into our favorite optimizer, and just get the next parameters, right? So that's pretty much it. So the inference time, I think we've already started discussing like what do we do after, like once we get these ST, right? So so the sampling, it looks like integration of an ODE. So we learn this function ST, we plug in there our vector X, we take the gradient and we get the velocity of this vector. So we can just, let's say we do like the earlier method, just integrate like with the most straightforward ODE integrator. We just plug in xt or like x0 that we got from like starting sample. We plug it in S, take the gradient with autodiff, multiply by dt, add to the previous point, and we'll get the next point. We do it, let's say like 100 or 1,000 times, and we'll get our curve. So visually it will look like this. So let's say we have the data. Here I plotted only for like 6 time points, but you can think that like we have like for any time t we have the data. And then we learn action matching by minimizing the objective that I told you before. Then we get the samples from initial data, okay? And then we start integrating the ODs for every sample on this scatter plot. This is like a scatter plot, right? So every dot here corresponds to like a sample. So we start from these guys, and we do like integration from 0 to 0.2, and we get this one. So this is another one, and we integrate further. We get this one, and this one. So you see that like we perfectly recover the marginals, right? Starting with some data, and we once again we have access only to samples. Sorry, I have to use the OD.
Then can we maybe have a question by Gabriele?
Thanks. So yeah, I had a couple of questions on the training objective. I guess the simpler one is, what is the relation of this objective? I mean, it looks a lot like implicit score matching. Do you have an intuition of the relation with implicit score matching?
Sorry, I'm not sure I'm acquainted to implicit score matching. So what's like, is it the original score matching proposed like in 2011?
So the explicit score matching is kind of like, it looks a lot like, you know, I guess the your original term, and then the implicit score matching, it's basically what you do when you can't have access to the score directly.
Oh, I think okay. So I think by explicit you mean like L2 norm from like conditional score matching.
Yeah,
when
that's
we know
the explicit. Yeah, that's an explicit.
And the implicit is the original from the yeah. So the difference. Okay, to highlight the difference, I would say the following. These are solutions to 2 completely different problems. Score matching solves the following problem. You have a distribution, you want to estimate gradient of log density, but you have a single distribution, right? And you can solve it. Like in theory, like let's say like just like with infinite amount of samples and compute, blah, blah, blah. So you have like nabla log density from a single distribution, right?
Yeah.
You don't have any process going on, right?
Yeah.
And even if you do, and you have like, you can recover this score for every distribution you have for any time t. If you have access to scores, nabla log density, it doesn't mean that you can perform kind of like sampling. It doesn't mean that you can propagate your samples between time, because you don't know what's happening to them, right? For example, just think about this. I know, like you cannot do something like this from like scores. I mean, like it's not clear. So actually,
yeah, no, of course, it's definitely more general. But I guess kind of what I was going
no, it's not about generality. It's about different problems. That's what I want to highlight. So you cannot formulate action matching for a single distribution, because you should have a process, right, going in time.
Yeah, but like, I mean, I guess with diffusion, you also have a process that goes in time, and you have defined your forward process that goes in time, and you're trying to learn the vector field of that process.
Yeah, that's true.
Maybe
so I mean,
can I
guess
interrupt so for everyone to follow, and also maybe to synchronize the question? Like Kirill, now have you gotten entirely what's meant with, or are you sure you have gotten what's meant with implicit score matching? Then can you
with implicit score matching is the original paper where like score matching was proposed, right? That you write the objective, which is like q nabla log q and then the L2 norm between nabla log Q minus your parametric family, and then you can like take integral by parts, and just from samples you can recover nabla log density, the score, right? And the problem is essentially like static, right?
Okay, so you're saying the difference sort of is that we're not looking at that we're only looking at learning the score of a static density at a certain point in time, but this density also changes over time, right?
No, yeah, I'm just okay. To be precise, the like score matching, it's I think there is like a confusion. Okay, score matching is a method how to take density and learn like original score matching, implicit, what you refer to as implicit score matching, how to take a distribution and learn gradient of log density, which is score, right? And then people who were like trying to develop diffusion models, they went and they're like, what if I have a diffusion process that I specify?
Actually, can I stop you for a second? I think, Alice, do you have by any chance the at hand the implicit score matching definition? I think we are talking about different things. That's why I think there is a confusion. So what people call implicit score matching is basically a way to train, like similar to the way that you train with like, it's not kind of the original, it's what you use as an objective to train a diffusion model. And instead of having the explicit score matching where you do the difference, you now have instead, it's like I think it's like you're minimizing the expectation of the score of what you have plus the divergence, the square of the magnitude of the score squared plus the divergence. And so it has basically very similar form from the objective that you have. So that's kind of why I was asking that question. Sorry, Anas.
Which paper, Gabriele?
I mean, for example, even for example, in the Riemannian score matching paper, they use implicit score matching.
Yeah, maybe I'll just open the paper.
Yeah, but I guess kind of related to this, it's not necessary to go out. The kind of follow-up question was, do you have an idea? So here, obviously, you have the same minimum. You have that when you obtain the minima, you exactly recover your distribution. Do you have an intuition when you're doing action matching of, if you have some error, how does the error kind of like translate into like error in the distribution that you're learning and in the process that you're
so I think there is like an misunderstanding that like we are like trying to learn some distribution, but we don't, like, and that's like a very different problem from learning something about distribution, because you learn something about the process, how the distribution changes, but you don't know what distribution is. You can bound the error in the following sense. You can like by the I have to share my screen once again, but I found maybe I should also, okay, let me. So this is the paper where score matching was proposed. And I believe that you're referring to implicit score matching to something like this, right?
I don't think so, but anyway, I think maybe we can take.
This is not.
Why take it? Don't take it offline, please. This is the purpose of these meetings, and we don't want to.
Okay, so this is not score matching, implicit score matching you're referring to.
Oh yeah, let me see.
Because this is what you said, right? It's like
it is something like it is something like this. Yes.
Okay, so this is what should be called the score matching. This is original paper where score matching was proposed in 2005. And the problem that people approach this person approaches here is we are given with a distribution of samples, and we are trying to learn nabla log density. And then people started like, okay, let's do this for every moment of time and so on and so forth. And like once we know the score, because we know the Fokker-Planck equation and we know how do we design the process, then using the scores, we can recover the process and go from one distribution to another. That's okay. So like, I hope it at least clarifies something about your question. Okay, cool.
This is, by the way, Gabri, also what the Riemannian score matching paper cites. Explicit score matching.
Yeah.
Like this.
Yes, sorry, just maybe to help us build intuition again, just if you get a little bit back, not in the terms of slides, sorry, but the types of problems we are talking here, if I understand correctly, are those where we have a clear time evolution with a clear start state and possibly even a clear end state. So I'm thinking about something about, I suppose, like cell differentiation from one particular cell type to maybe a bunch of various cell types. Because like the most problematic thing for me is how to discretize time in such a way that independent batches would actually coincide. Like we do not know if the batch, one independent batch actually occurs at the same time, right? As the
I think you're referring to what I've discussed like in the very beginning, the motivation of the problem, where like we observe uncorrelated samples from some process, right? And this is like exactly like single cell biology and these like trajectory inference in single cell biology, right?
Yes, for example.
Yeah. So exactly. So that's what I'm saying. They like to compare it with score matching, we have to understand that the problem is different, because the problem is that like once again, okay, let me go to this slide.
So basically, if we would ground it in our familiar, like, let's say, image diffusion models, instead of having one general data distribution that we are learning for all kinds of images, we now actually narrow ourselves to a particular sort of videos, and videos where we start, for example, with noise. Okay, maybe that's a bad example because it will be like we start with an, I don't know, nature scenery, and we slowly convert it into technological scenery. And basically because of that, we have at each time iteration, we have the distribution of the image changing more or less predictably. And we are now trying to learn the change of this distribution.
So you can take it to the kind of space of videos, but you can also think about this in the context of like generative modeling of images. And I would say that this would be less convoluted. What I'm trying to highlight here is that the model doesn't learn anything. So here we are like generating these diamonds. What's essentially here is that the first scatter plot here is blue one. And it means that our model doesn't generate data at time point 0. The only thing it can do is to take the data at time point 0 and kind of predict what the data is gonna look like at time 0.2, right? So it changes, it learns the change of the distribution. And if you think about it, it's not related to the distribution itself, because I can tell you the change of the distribution might be a drift, right? But the drift might change any, so you can like here I was like here the Gaussian is drifting, right? But you can say like a mixture of Gaussian is drifting, but you would learn the same model. If anything like complicated, like insanely complicated is drifting here, you would learn the same model of the drift, right? You don't learn the distributions, you learn the change.
Yeah, I actually understood this. I was more like trying to have a more clear analogy. But okay, let's not waste. Maybe one last analogy would be somewhat similar to learning, let's say, like potentials for some molecular dynamics simulation, where, for example, like yeah, we have time frames, and maybe we first learned, like, I don't know, coarse-grained representation of a data, and now we are trying just to learn how in this coarse-grained representation we will actually evolve the system so that it will be faithful to the atomistic simulation. But anyway,
I think that's exactly the point, that's not the case, right? We are not learning a potential at a certain point in time and then learning another potential at another point in time. And then we're sort of doing Langevin dynamics or annealed Langevin dynamics with these potentials. Instead, we're only learning how the distribution changes. So I think this, Kirill, is that the point that you wanted to make with the implicit score matching versus action matching? In implicit score matching, we sort of learn an aspect of the distributions. And sure, we have multiple distributions because we have different distributions at every point in time. But how we then evolve our samples is we use this aspect of the distribution and run our annealed Langevin dynamics to end up with samples. But here we really learn the vector field with which the distributions change.
So yeah, I'll try to, like, first of all, about the dynamics, Denise mentioned the potentials. It depends on the problem statement. If you have trajectories, then you can like do it like in a different way and learn the potentials in a different way. Here we also kind of like trying to learn. You can also potentially do it for physics and learn the potentials there, so on and so forth. For like, yeah, I think I also see like some questions in the chat asking like the diffusion models do the same. The difference is that like if you want to, diffusion models essentially they know what's going on underneath. They know that this is like, okay, this is like a Fokker-Planck equation, and we now need just nabla log density to kind of like turn it into like an OD and like integrate backwards. That's what they do. Here we don't have these assumptions. I'm just saying that like for like answering this question, probably question of Garrett on the chat, is that imagine that you don't know anything about your process. You just have like a black box that outputs samples. You put time in the black box. In this black box outputs an independent samples from the distribution at this time point, right? You can, okay, you're gonna learn the scores with score matching, for example, but then what you gonna do with these scores? How you gonna like propagate your samples between them? That's a different problem. I'm not saying that like it cannot be solved. Maybe you can come up, because you can like potentially, let's say, start like a Langevin dynamic and like anneal it, and that's what we actually compared to in our paper as a baseline. But I'm saying that that's then you have another problem, how using scores sample from different marginals. And here we kind of like we solve this problem immediately, not learning the scores and not learning anything related to scores. Because once again, like for example, like for this drifting Gaussian, right, we can know the scores, but then like what? How do we like propagate? We don't know the drift, for example. I mean, we have to take a look at the equation maybe, and then like figure out that, oh, this is just a drift, and we can like perform it, right? But then we can't really, because we just have like a black box out spitting out the samples, and we want to learn the change from this. But maybe we should go further, like, and like go to like applications. Sorry, I skipped some questions on the chat. I just Yeah. Yeah, so another question is that people are not convinced in the uniqueness of the fields. Yeah, I think I can give a couple words after the talk about this. And what factors you choose to implement the code in JAX rather than other frameworks? I think that's not related to the current discussion because the distribution is changing its parameters. Is necessary because the support of distribution is not the only reason to choose these. People are asking, is the support is changing? So here the Gaussian has like infinite support, and here no support change happening. Like the support is always like a Euclidean space, right? So it's not necessary, but it might help actually. So from practical perspective, yeah, this might be the case. The analog of the vector field motion analog in neural networks. So yeah, so vector fields motion is like how in neural networks. I think we'll go to applications and examples with images. Maybe it will become more kind of clear. Okay. We went over this, over this, then like variations. Yeah, okay. I think given the time, I'll kind of go quickly through variations. What I want to show here is that instead of continuity equation, we can assume that we have like Fokker-Planck equation on this kind of like underlining space, and we have some of these like stochastic part, and we add some noise on the way, and we can also like with this assumption we can once again solve the problem. The only thing will change. So this is the original objective function. This thing will add. So it's very simple. It's very like extendable in this way. What I want to highlight is that the marginals don't change. So the only thing that changes is the trajectories of individual samples, right? So here you see that like they go kind of like in a deterministic way, integrated by OD, but here they are like stochastic and they kind of like yeah, they run around on the way, right? So because we integrate like in SDE, but marginals are fixed. What we change just the notion of the underlining process, and we change the notion of remember we chose the minimal vector field that does the job. We can choose a different one in a way. We can choose like a stochastic process, minimal stochastic process that does the job, and learn this from samples as well, like just from samples, from marginals, preserving the marginals completely.
I'm a bit confused. Like, how can it still be minimal?
Oh, because now it's minimal in the family of stochastic processes, not in the vector fields.
Okay.
It's like a different concept of minimality. Okay.
Yeah.
So because minimality is actually the it's a concept like from variational calculus, and this like minimization of some Lagrangian, but you can define like different costs, if it makes sense, different losses in a way. We can also like do like we can give like magic powers to our samples. We can let them teleport in space, which is kind of like fun. So we will add this like growth rate. In optimum, it will be like this, but this is like once again like a detail that you can learn from the paper. The loss, once again, we have this original loss. Bam, it changes just add this and you'll get this. The only other thing you have to change is how to integrate, because now besides propagating the samples in space, integrating them, you also have to track kind of the presence of the sample through the weight of the sample, so it can actually teleport. And just to give an idea, what does like teleportation look like? it's usually we think about this. So we just like rearrange the samples in our space, right? But teleportation will do something like this. So you see that we can fit to the kind of right Gaussian, not like there is no mass at any time of points in this space, right? The mass just teleports to the right.
And in this visualization, you're still just integrating the ODE.
Yeah, just extended ODE because you also have weights.
Okay, and then just the weights in the beginning. I can't quite get this. So do we then have in our vector field just super large jumps and this sort of teleportation?
No. Instead, you do the following. You say, okay, it's like you combine importance sampling with other like sampling techniques. You think that like, okay, I have like samples, I can rearrange them in space according to my vector field, but I also kind of like put weight on every sample, kind of put their like value of the importance value of this sample, right? And this also changes in time. And here, what essentially happens is that like here, the importance value of samples is 0. But then they can like kind of like go to the right and then increase their importance value.
Okay, so we already have. Yeah.
This is like you should think about it as other kind of ways to like is as a way to extend the continuity equation by considering like different like dynamics, what can happen to samples, because like you can think of like different things that can happen to samples. We can just rearrange them in space, we can rearrange them randomly, that's like a stochastic process, right? We can rearrange them and give like weights. We can probably do maybe something else, I know.
Yeah, so we additionally learn a weight here, right? And the weight also.
No, that's actually like, I know, like this is like magical. This is like marvelous because the function S is the optimal weight. It's yeah, it's I think it has like deep connections to these like geometry of like Wasserstein manifold, but it's very interesting. But function so kind of it gives the meaning of the value of the absolute value of function S. Before we were using only the gradient, right? And the absolute value doesn't matter. But now the absolute value matters because we use it as a weight.
Okay.
Log weight to be precise.
And is there then anything about having a constant added to S?
So before you could add any constant, now you can't. Well, in unbalanced setting. So okay, just to make a teaser and like motivate you to read another paper. That's exactly the intuition that we have in this like Wasserstein quantum Monte Carlo paper, because what's on the right is like what's happening in like kind of standard variational Monte Carlo algorithm, and that's what's on the left is what's happening in Wasserstein quantum Monte Carlo, which is our like recent paper at NeurIPS, where we find the ground states of like physical or ground states of some physical systems.
So we additionally now look at the output of our S and not like of our S theta, and no longer at only the gradient of S theta. And this then tells us how what is the weight of each of our x's, and then we assign this weight.
Exactly.
Okay, and then what's happening here in your visualization is that while like sort of the animation on the right, on the left is also happening on the right in the background, but while this is happening, the weights for like while the thing is in the middle, like while the right cone is still traveling in the middle, it has 0 weight, and only when it arrives, so to say, the weights are increased.
Okay, so in these animations, I just wanted to highlight what does teleportation allows you to do. What does it? What can you like? What magic abilities allow you for? So it's on the left. We can only transfer samples in space via a vector field. Okay, and there is no way we can fit this orange Gaussian to the right one, not crossing this kind of like value of 0 density, right? Does that make sense? Because I mean, like we start from the left, we have to transport something to the right. So at some point we'll have some samples here, right, in the middle. So,
but I mean, yes, but in the thing on the right, I still have in your teleportation video here, I still somehow need to get my X from the left to the right, right? And
that's on a computer. Yeah, yeah, that's true. That's true. But that's on a computer. You can think about it is that like these samples, like sometimes they can once again, it's they can give you like different trajectories if it makes sense in your like scenario, in your case. And okay, think about this one, like single cells. Now the marginals, they like the cells, they can like divide, like they can like specialize, and then like some of them they can die, and some of them can grow, right? But it doesn't mean that they kind of like exchange cells, right? It's not that like one cells become like change the speciality, right? Instead, they just like one's die, one grow, so there is no continuous flow of cells in between. So if you don't include this teleportation in your model, you won't be able to model precisely this process of cells evolution, right? But if you include, you can. And that's a point of like our paper that we haven't put on our archive yet, but we're gonna do it soon. And there we show that like if we do these like unbalanced stuff for single cells, we actually can gain some performance.
Okay, but here
So
when we
about,
integrate the
yeah.
ODEs, then if we only integrate the yeah, like while integrating the top ODE, we're still moving across this area with a low probability.
Yes,
But
yes,
while
yes.
we're moving across this area, the mass that we assign to the sample is just very low.
Yeah, yeah, exactly.
Okay.
Yeah. And once you want to sample from your model, you're not gonna sample from this area of low probability.
Yeah.
Right. Okay. So let's go to some results. If we still have time, how do you feel about it?
Yeah, we have time. It's about your time.
Oh, okay, okay, nice. I also have. So yeah, this is like a synthetic example just to give an idea what's happening. So you have like data which from different like days in color, and that's the only thing you have. And you want to recover the trajectories from these data. As I mentioned before, this is like important for like building the model. How does cell evolve? Okay. So we can get some numbers here. I'm not sure they are like very elucidating to the algorithm, but this is like one of the applications for, and this trajectory inferences is very active area in biology. Another example is like a quantum system where like, this is like a 3D, okay, this is an excited state of a hydrogen atom in 3D projected on different planes. And you should think about this. We take the hydrogen atom, the excited state, we propagate it up to some time, we measure it, we get a sample, we repeat this process many times, and we collect these samples uncorrelated over time, and then we train our model just from data, just from samples, and we can then take like a sample from initial state of the hydrogen atom and just propagate it in time and get a sample from like after a second or like 2 seconds, whatever.
But we cannot take 2 measurements, right? Only one, because of uncertainty.
Sorry. So we cannot do 2 measurements because like the system can already collapse.
Commutator, right? Because to do 2 measurements, you need to also use inductive bias for the commutator of the observable effect. But okay, I understand that this is only 1 measurement, and I just wanted to ask that.
Yeah. So this is like, maybe don't give it too much thought. Like it's just an example. Like, so let's say we have like a quantum system, and I know you built a quantum computer, and now you want to try to understand if it's good or bad. Like you have some like blueprint of quantum computer. You have your quantum computer. How do you make sure that your quantum computer corresponds to your blueprint, right? So that's what you can do. You can take a lot of measurements of your quantum computer, right? You can learn this thing that kind of propagates them in time on a classical computer. You can from then actually you can recover the Hamiltonian and compare it to the blueprint and say, okay,
I thought that's an EPI problem. I thought that's really complicated. Like trying to learn the Hamiltonian, it's not trivial. Like it's not. There was a paper recently that is a polynomial, like up to some orders and some information of the Hamiltonian. You can downscale it to a polynomial, but it's still like pretty bad.
So I'm not providing the like asymptotics of complexity here. And usually these problems, they have like a lot of context on top of them. And I'm kind of like skipping the context and giving the like example, right? To try to explain people the like the algorithm. And I believe what we were talking about is maybe about like discrete states computers. And here it's just like continuous state with the system. And of course, I'm not mentioning the like computational power, how many samples do you need and so on and so forth. I'm just trying to explain kind of the idea of the algorithm that I'm describing.
Yeah, and I think thanks for that. And maybe this is like getting a bit into some quantum details now, and not entirely. Yeah, if you have more questions on that, maybe these are the questions that we can take offline, and we can focus on the action matching part of this.
Okay, so let's go to other examples, because generative modeling, I think that this is more kind of like it's much closer. You know, all like these like different algorithms for like image generation. We start from some noise, we arrive at the image. Here, because we need only access to samples, we don't know, once again, like the algorithm doesn't know anything about the process. So here I'm just writing the sampling process to kind of explain what's going on the left, and the algorithm doesn't know anything about what the sampling process is. So we can do like super resolution, which colorization, you can start with a grayscale picture and like go all the way to the color picture, and you can get some results. So here for generation, for like super resolution, it works very well. Even though like here, like I actually, this is a wrong picture. I remove more pixels. I just like leave every fourth pixel. So for generation, it's worse than diffusion models, original diffusion models. It's like, I know the original model is so good. It's 3.7, but if we just compare, not in terms of FID, but like visual generation, it's not that far. So it's not like that bad that like it's not applicable, you know. It's there are like pretty decent, it's the same generation from the same seed. There are like differences between, because they learn a bit different vector fields, and they also like the, of course, the different objectives, and learned at different quality of images, but it's pretty close.
Kind of amazing to me. Like we only like we only look at intermediate samples. We don't have this like in a diffusion model where we already know the drift, and we have the drift, and we defined our forward process, and we know what this forward process is, and we know that we had this like adding noise to end up
Yeah,
with the station
yeah.
distribution.
Thank you, Hannes. I think it's very, it's yeah, it's a very good comment. I'm just like rushing to the end because I was afraid of like being too late. But yeah, you have to understand that like diffusion models here, they design the process. They know like how do we change the data to the Gaussian, and this is a very significant degree of freedom in generative modeling that you actually have to use. And this is like very good that they use it. What I'm showing here is that even if we remove this degree of freedom, we can learn a lot. And this is, I think, kind of shows the power of the method, that like just completely abandoning this approach of generative modeling, that we can actually design the process of distorting the images, and we know this process. Just removing this knowledge completely, we still can learn a model that perfectly restores this distortion process. Because for generative modeling, of course, you should know, you know the process of distortion, and you should use it, and you should use generative modeling. But there are like many cases, as in biology and in physics, where like you don't have access to this distortion process, and that's maybe what you actually want to learn, right? And yeah, I'm really like hopeful that like if it scales to like images in these like high dimensions, then I think we can like find like some cool applications in natural sciences for this.
Because to me, it was sort of my thinking always was, yeah, if you have this intermediate, or this is cool, this is something you proved that you can do it, and that this thing is unique, and yeah, if you perfectly train with large blah and have infinitely much training data and from all of your intermediate samples, then sure, you can train this thing. But now we actually see that it works quite well, and this yeah is surprising to me. But yeah, we also have to consider here, right? You have at every single point in time, and yeah, samples at every single point in time, and you can like close the gaps, all of the gaps. And maybe if you have your single cell stuff, then might be much more problematic.
Yeah. So answering another question in the chat, which part of action matching corresponds to higher FID values, lower? So once again, these methods, yeah, I have to mention like rectified flows and flow matching, which is like tightly related to this. But they rely on the process as we discussed. So that's one of the sources of like better performance, lower FIDs. Another source, in my opinion, is the architecture, because that's that's a difference with this method, because like this method, they learn a vector field, they parameterize a vector field, right? So they take an image and output an image, right? Here we parameterize a scalar field. We take an image, we output a scalar, and then we take a gradient of this function. And this is like essential for the algorithm, because like to simply write the objective. And I actually experimented a bit with the, I just took UNAT and then like I chopped off the hat and like was outputting the scalar. And this works worse than just taking UNAT, outputting the image, and then taking a scalar product with the original image, which is kind of like a dirty trick, but it works a bit better. But yeah, answering the question, one thing to explore is maybe the architecture, because I haven't explored this enough. And people clearly tuned the architecture of diffusion models to parameterize a vector field. And I think people haven't really like thought about how to parameterize a scalar function to take a gradient vector field for images, because it wasn't really necessary.
Yeah, sorry, but if I understand correctly, does it mean that if you can parameterize your vector field with a scalar function, then essentially this is a conservative field, so zero curl, so essentially you expect convexity, and this means that you cannot like have unexpected fluctuations along your time evolution trajectory. So in terms of cells, for example, cells cannot like stochastically jump from one cell line to another one, right? They are sort of predictably moving from one cell type to another cell type, and you cannot have like in between transitions.
True. The problem with these, that like once again, like the question was like specific to images, and that's my intuition, because like unfortunately it's also like it's a hard question that people study like separately, how to like parameterize these things, right? Like how to design an efficient ansatz for your problem. And for images, the question is like the answer is like you parameterize the vector field with UNAT. Here we have to parameterize a gradient vector field. So I just like in what time I had, like I just took and designed something, and yeah, it works somehow, but I haven't explored it.
Yeah,
but
but
maybe for single cells it makes it works. But once again, I didn't put enough thought into, because it's a separate study. Like you have to, I just took MLPs like for single cells, and it worked. But maybe you're right. You have to like maybe that's even better for like single cells. And but once again, you have to study these questions.
Yeah, like to be fair, my question was much more like simpler. What kind of limitations on the vector field this possible scalarization of the function
So
that produces the gradients? Yeah.
Yeah. So the question, the limitation is, I think, in terms of ansatz, it might be not as expressive as like parameterization of a vector field. But once again, given the problem statement, we know that the ground truth is a gradient field. Okay. And in that sense, if you think that your ansatz is good enough, you should be recovered. Like, let's say you take, once again, let's say you take like very like powerful like neural network, you have enough data, then you have to recover the ground truth, right? And if you come up with a different objective, but like that also has this ground truth as optimum, but you parameterize a vector field, you'll recover the same vector field. So because the problem statement is like the gradients, the gradient field is the answer to the problem.
Yeah, okay, thank you.
Because yeah, so if you want to include some like curls, the problem with curls is that you have to like specify the cost of it pretty much, and this would be like a different maybe
Yeah, like
you have to optimize.
Like what I just don't understand, like in terms of rectified fields, rectified flows, sorry, they are operating on just the data space of images, right? There is no like intrinsic complexity to the time evolution. All what they are doing are just assuming that they can have a linear interpolation between the noised sample and the recovered, like closer to the data distribution sample. But here, if we are trying to do the same for something that has unpredictability, like basically diverging paths, because obviously this would not work. So it would not work for a lot of various time evolutions distributions.
Okay,
and
so
here I just want to understand if this is sort of in terms of its expressivity, if it is similar or if it is higher than rectified flow in a sense.
I think you're like trying to incorporate some background knowledges in your model, and like my answer would be to your question, you have to go back to the first kind of point of the list, to the problem statement, and incorporate it there. You first have to incorporate these backgrounds, prior knowledges, like in inductive biases in math, and then you can incorporate them like at the architecture. I think you're like kind of like skipping here like important part, which is the problem statement. And there you, yeah, because I once again, like the third point, like the variations of action matching, they are demonstrating some possibilities to incorporate some of the background knowledges, like stochastic, this jiggle of cells, or growth rates with which cells die and can like be born, right? So these are ways to incorporate background knowledge, but we do it first at the like the problem statements, and then we kind of get. But in these cases, what we get is that the parameterization of a single scalar function is enough to incorporate these particular inductive biases. If you want some specific one, you should like probably come up with a different cost, or like different equation for the change of density, right? And maybe then, yes, the answer to your question could be potentially that you have to parameterize a whole vector field that can have curl.
Okay, thank you.
I want to say a couple words about relation to optimal transport. This is how we posed the problem originally with the kinetic energy minimization, given the process. But we can also take a look at the dynamical formulation of optimal transport. And here we will have these guys. So this is the only thing that's adds. So we now also take infimum with respect to the process with the fixed endpoint marginals. Okay. So you should think of it that like action matching can be thought as like an inner loop of dynamical optimal transport solution. So let's say I propose you a process between two marginals. Then we evaluate action matching, and then we can like minimize this kinetic energy. Yes, Hannes.
So, but like in optimal transport, we don't have QT given. We only have the 0, 1 marginals given. And
exactly.
Yeah, okay.
So that's why you have to optimize with respect to these processes, right?
Okay.
So what I'm saying is that like you can propose me a process, I'll do action matching, you can evaluate the kinetic energy of this process, tell you, and you're kind of, okay, can I take the gradient with respect to the parameters of this kinetic energy, with respect to the parameters of the process? And I can tell you yes. And you're like, okay, now I propose you another process. And we go back and forth. And this is also like, this is one of the things that we do in our paper that's gonna appear soon, but not only for optimal transport. So you can parameterize this process with the neural network, and then you can do kind of optimization with respect to the process itself. You can also think that action matching actually learns kind of the optimal transport plan between two infinitely close distributions. So you take qt plus delta t, and then once delta t goes to 0, your optimal transport plan, it converges to this Lund vector field. So if you think about like what's happening, because once again, we fixed the marginals, but we didn't fix how we go between them. And the answer, we take any two like very close marginals, and between them we do optimal transport. That's there is a whole mathematical area which is called autocalculus. It's quite recent, it's super beautiful, and this is essentially a differential geometry on the space of distributions, but not like information geometry. It's a geometry, it's a bit different, with a different geometrical structure, where the geodesics are given by optimal transport, actually. So the straight lines here on this is like a manifold of distributions. Every point here is a distribution that corresponds to this kind of blob on the state space, right? And the straight line on this manifold is an optimal transport. So this is a geometric perspective of action matching. It is as follows. You imagine that you're like given a curve on this manifold, okay? This is a stochastic process. Like your distribution changes in time, right? And what you learn kind of like the tangent vector. But to be precise, I'll tell you, I'll say it, but you shouldn't be like afraid of this. We learned a cotangent vector, because the tangent vector, as I think as was mentioned before, the tangent vector is d rho t dt, okay? And to parameterize it, we have to put some constraints. For example, this it has to like integrate to 0, right? Because the total change of mass should be 0. Then if you have like 0 density at some point, you cannot put negative change of density there, right? You cannot subtract mass from like 0. So there are some constraints to these tangent vectors. That's why instead of parameterizing tangent vectors, we parameterize cotangent vectors, which are vector fields. Vector fields is very easy to parameterize. You can just say, okay, this is my function, and samples go this way, and that's it. And for any curve on this density space, just collecting samples, you can recover the cotangent vector at every point of this curve. And this is geometric message of action matching. So this would correspond to this nabla phi t0, nabla phi t1, nabla phi t2, and so on and so forth. So a bit of a teaser to our next paper is that this corresponds to minimization of some Lagrangian. You fix 2 points, you define a Lagrangian. So every curve has a coast, which is action, this function S. And you integrate over the curve, you get the cost, and then you minimize it, and you can get like OT distributional plan path. you can also define a different Lagrangian and get a different curve. And you can put marginals as constraints, and you can build kind of like splines in this space. So you can like have like 3 points. Now you don't have like dense curves, right? That's kind of our next step, what we were like wondering about next. We have these kind of dots, and we want to interpolate between them. And you should think about like time series interpolation, really. Like it's just like you have like dots, you want to build like a spline, build a model of this time series, right? So here we do the same, but in the space of distributions. And we have to introduce some notion of like optimality of this path, which is Lagrangian. So I know like the magical thing about this is that it's not only about optimal transport. You can write a Lagrangian, so in between you get a Fokker-Planck equation. Moreover, you can write the Lagrangian, so in between you get Schrödinger equation. So you kind of say, okay, I have this guy here, but in between there should be, they should evolve according to some Schrödinger equation with a given Hamiltonian. And this is like, I know, yeah, I think it's very beautiful because it unifies a lot of different processes in a single geometry. It's, I know.
So
Yeah,
does it then mean that I can learn a Schrödinger bridge where the reference paths or the reference path distribution is not just Brownian motion, but instead it is like the dynamics of this Hamiltonian that you mentioned?
okay, so the Schrödinger bridge is when you fix the distribution and in between you have a Brownian motion, right? But kind of like optimal Brownian motion because like it's entropy regularized optimal transport. But
Yeah.
Answering your question, yes, you can do like the Schrödinger bridge because you can get like 2 distributions, and in between you can put like a Hamiltonian, and the path should satisfy this Schrödinger equation. Yes, you can do this, and that's what I was like wondering about last month. Like, so this is like an extension of optimal transport to the space of physical like processes. You can introduce some potentials, or you can do like many different things. Yeah. I hope we once again will do it like for like single cells, because I think that's the main application right now for trajectory inference. But maybe with time, we'll have more applications, and we'll have more interest in math and models for this. But yeah, you're right. That's exactly
Okay. Like what? Oh, this is such a painful teaser. When so did you already submit this to archive?
Yeah, no. Like it's gonna appear this week. I'll promise you.
Okay. I'm pretty excited.
Yeah.
Good.
So you can find more in the paper. As I've mentioned multiple times, this is like an active field in biology, and there are like much more. If you're interested in these like trajectory inference single cell, there are like tons of good reads. I think we answered partially some of the questions. For example, that like these like presence of curls and so on and so forth. Yes, so you can like do like a Hodge decomposition or Helmholtz decomposition, but multidimensional. And you can recover the like action matching actually recovers the minimal vector field, which has no curl, as was mentioned. Don't be afraid to go over proofs. They are quite simple, and they require only, I would say, like basic calculus, like first year calculus. I prepared some tutorials where you can like open a notebook and play around with it, and there is JAX implementation. People ask me like, why did I choose JAX over other frameworks? There be like unpaid advertisement of JAX. I love JAX because of its like laconicity. Like I'm not sure. It's very like concise. It's beautiful. You can like if you have to do one thing, you know how to do it. But also you can take a lot of derivatives, and I've been taking a lot of derivatives through the whole talk, like gradients there, then like one more, and I did it in PyTorch as well first, but then I re-implemented everything in JAX, and it became so beautiful that I was ashamed to publish PyTorch repo. I hope you'll forgive me. But if anyone wants like a PyTorch implementation, I'll share it with you. You can write me. Yeah.
Then we have the very important question from the chat. What was the name of this information geometry-like thing that's not information geometry,
Oh
but
yeah,
geometry?
it's called autocalculus. It's Felix Otto. Kind of okay. I'm afraid to not mention some people. Because there are like a lot of beautiful works. Figali recently, I think, in this topic, he received like a Fields Prize, and this is like an active field of research in math. But the first works I've read is like Felix Otto. He wrote like a PhD thesis where he proposed like a differential geometry structure for these vector fields and the continuity equation. And the continuity equation, it's a beautiful like, yeah. I think this is like, this is a good maybe a link to start from. Gradient of Wasserstein distance in the states of autocalculus. This is a good start, yeah. And then after reading this math overflow link, you can read our paper on Wasserstein quantum Monte Carlo, if you wish, because that's exactly what we do just for quantum energies. And yeah, there is like a huge book by Ambrosio. We give a link to it, like a reference to it in the paper. It's like fundamental on like gradient flows, and they introduce like, so like, I know like I cannot sometimes read it because like it's just like it's so formal, but you should definitely give it a try. Some parts that you're interested in, how to define a gradient flow, for example. That's really cool.
Okay.
Yeah, this is the uniqueness proof. You can just assume two different things and then just show that this should be equivalent. Some I remember someone was asking, yeah. Let me know if like don't hesitate to approach me with any question. I usually answer everything pretty quickly. And thank you for invitation, Hannes. It was a pleasure with all these questions. I think you created like a really nice environment where you really it's a nice thought provocative like research discussion. I really enjoyed it.
Yeah, and I really am glad that we sometimes have like speakers like you, where we really have some great discussions, and everyone's just very interested in the topic, and there's a lot to talk about. But then I would like to it's already been 1.5 hours, but I would like to get to two questions.
Of course,
And the first one is getting back to this learning a score, for example, versus learning the vector field, like the vector field with which our distribution changes. And now, what is the relation to, right? If we do flow matching, there we also would learn like, of course, we know there the reference process, or there we know the dynamics, we define them in some way, but we just the quantity that we learn, so to say, is the same, or no, the quantity that we learn is the same, except that here we just learn a scalar function and then take the gradient.
Yes, so it's not exactly the same because okay, I'll just cut some corners, but the answer to this. So first of all, rectified flows, flow matching, like are beautiful works. like it's so like concise and like simple and at the same time beautiful. They rely on these like underlying process. The main difference, I think, is that the ground truth vector fields is actually different. It might have some curl, and in that sense, if you learn a vector field from flow matching or rectified flows, and then you do Hodge decomposition, you project it to the space of gradient fields, then you'll get the same vector fields. But without this step, you'll get something a bit different. You can actually like, I think this is kind of, I think this is for some reason, I think this is not well-known thing, that you actually can derive the optimal vector field, the vector field that satisfies the continuity equation. Wait a second. So it will look something like this, where this like QTI is a little Gaussian around every data point, and you can like get a formula from this. Okay. So moreover, I think correct me if I'm wrong, but I think this paper is called like physics-inspired generative neural network, where they kind of like they derive the formula for the vector field. Then they take like a huge batch, and they learn just from samples, and it also works. And then they have like a follow-up physically. It's not pins. I'm confusing things. They take like Laplace equations from like electromagnetics, and that's I think this line of works is from MIT, from the group of Tommy Yakola, and there I think they use something like this, like a different formula, because they have like a different process.
Croissant flow generative models.
Yeah, I think so. And then this vector field, you can actually take a look at it and think if like in some cases it is a gradient flow or not. And that's what these models learn, and that's what rectified flows, flow matching, and this line of works with electromagnetics, they work. And to get the vector field that you learn from action matching, you just have to do like a Hodge decomposition and project it onto the family of gradient flows.
Okay. Wait, if I do that, let's say I do my Hodge decomposition, and I also I never I don't know Hodge decompositions and what would be required to know to actually do it in practice. But if let's say I do that, do I then end up with no, there's no optimal transport stuff here, right? Because it's just still with respect to this reference flow that we defined.
Yes. So to get to the optimal stuff, to optimal transport stuff, Chang Liu came up with a like beautiful procedure of this like rectification, where like you learn rectified flows, then you learn like you get the new couplings from the learned flow, then you linearly interpolate between them, and then you converge slowly like with these iterations to an optimal transport, which is, I find, like insanely beautiful. And
You mean
another like also like gorgeous work is iteration proportional fitting by Valentin de Bertolli, I think, and Arnaud Duché. I don't remember the authors, correct me if I'm wrong.
no, that's correct.
That's also do like Schringer bridge. in this way, they extend like rectified flows to Schrödinger bridge and show that you can actually do this for like Fokker-Planck equation and like Brownian motion, which is insane.
But with Liu's work, you now mean diffusion Schrödinger bridge matching.
No, I usually let us build bridges.
Ah, okay.
I
Yes,
think
yes.
this is a very good thing. Oh, no. Okay, so this is a different work that I also really like. It's perspective from Dub H transform and Girsanov theorem. But I think, okay, then it's just rectified flows. I'll just want to show one rectified flows.
You mean now means flow straight and fast, or yeah?
Yeah, maybe flow straight and fast. Because I think they changed the title from time to time. Yeah, so this picture explains everything. So you do linear interpolations, you learn your flows, right? Then you, since it's an ODE, you cannot have intersecting paths, right? Because they have unique solutions. And that's why they split here, right? So that's why this is happening. Then you do linear interpolation once again, and then you converge to optimal transport.
And like with linear interpolation here, you mean doing flow matching?
Yes. So I think this paper also proposed kind of like flow matching, but like, so flow matching is a part of their proposed framework, which they call rectified flow. So they propose this optimization of the vector fields with these guys, and then also this iterative procedure of like to get the optimal transport.
So I mean, yeah, they already proposed flow matching, but just as part of their procedure. But they actually also did more than what flow matching did, because they already proposed it for going between arbitrary distributions, while the flow matching paper that came out at the same time only went from Gaussian to some data.
Mm-hmm.
Yeah, anyway, then one more question about your the other question. This paper is called Flow Straight and Fast, Alexiga. And then we have our right. You have your new paper coming out this week where you do something where you can also learn a Schrödinger bridge with respect to the path distribution arising from an energy surface. Is that right?
Okay, so yeah, I think my co-author Rob, he added some slide. So on the left we have some examples of what we can do. We can we first, like, we propose this perspective that many different things you encounter, like optimal transport, entropic optimal transports, like unbalanced optimal transport, or maybe you want to combine like an entropic and unbalanced optimal transport, or maybe you want to add some physical laws to it. You can formulate from this perspective by introducing Lagrangians on the Wasserstein manifold, okay? And once you do this, you, in some cases, okay, so we haven't solved this for the case of Schrödinger equation. That's a bummer, and maybe we'll work on this like later. But you can solve for some cases where you have dependence linear in density. That's our algorithm, because once you have its linear in density, these Lagrangians, like the dual to these Lagrangians to be precise, you can propose like a simple algorithm. If they're not linear in density, you have to do like some gimmicks to it. I know. So here we solve these different problems, and we then approach like trajectory inference for single cells, where we try to because like trajectory inference, like once again, you can match the marginals, but trajectories can still be incorrect. So what you can do, you can like leave one out, one marginal, and try to predict, try to really kind of like solve the interpolation problem, right? By choosing different Lagrangians. So you can think, once again, it's you should think about all these in Euclidean space. You have a bunch of dots, right? You want to build a spline, but then your question is like, okay, which spline should I choose? And the answer is like, just leave one out for every dot, right? Build a spline and then measure the error. Does that make sense?
What do you mean with leave one out?
So leave, like, I mean, leave one out is like we remove, like, okay, we have like 5 dots, right? We remove one of the dots, use the rest as a training, and this dot as a test. We build a spline on the rest, and then test on this leave one out, left one out this point, right?
Yeah.
And we can do this for every dot. Okay.
Sure.
And that's how you can choose which spline to use. And that's how you potentially can recover the ground truth trajectories, because trajectories are like hard to recover.
Okay.
I think it's very dense to like I think my explanation is like, yeah, I think it's just like too much for this limited time. But the idea, yeah, so if you are to like draw some splines in your space, or like do some like time series interpolation, right? You have to choose the proper kind of loss function for this. And we show how formulate different loss functions and how to optimize them. And we show that they can actually improve the performance on these for the trajectory inference. That's long story short.
Okay. Well, so I now already have an intuition with what to about the procedure, with what to go into your paper, and I think then, unless you have any other points you want to bring up, we should call the day here and thank everyone.
Yeah, I also I'm really thankful to the audience being so patient to my kind of a bit hectic explanation sometimes. Yeah, just give it a try, like to rate action matching. I think it might look a bit scary with equations and stuff, but it's really, I try to convey the intuition here. And yeah, I hope I'll get the US visa and I'll be
like how they, you know, are these random, are they just playing out all the functions? Are they, how do they know that it's vulnerable? Is there, right? I think these are the ones like they're looking for like
I'm not sure if that was just some spam or something. I just muted him. Yeah, if that was not some spam, you can write in the chat and clarify. Okay, but yeah, what I wanted to say, Kirill, in your paper as well, it is you're saying flow matching is beautiful and super simply written and so on, but also I think in your paper it is like I'm not a mathematician, right? But what you say is really true, that the proofs are simple and the or at least some of them. I didn't read every proof. And it's really also a super accessible and well-written paper.
Oh, nice. That's thanks to my co-authors. I think Rob and Ali, they did a great job on like writing, like interpreting my thoughts with English, you know, like, and we went over like proofs and texts many times. We had like a first paper, first draft, then we reworked it completely, and so on and so forth. And we had like a lot of discussions, a lot of time spent on like presentation, and maybe I think I know, like I feel like we could do even better job, and I'm trying to kind of catch up with like doing like trying to do like good presentations. But thank you, that's flattering, and that's also due to Ali and Rob, this whole presentation. Yeah.
Yeah, I think it might not be so obvious how much this pays off, this sort of or well writing and investing in that and making it
Oh
understandable.
yeah, yeah,
I think in the end, it actually, like in terms of people using your stuff, I think it pays off a lot,
yeah.
because then the barrier to entry is just much lower. So thanks for that.
Yeah. I hope I'll also be able to present Wasserstein Quantum Monte Carlo at NeurIPS, where we got a spotlight presentation. And for people who, okay, so here I talked about how to do these like curves and splines and blah, blah, blah. But what if we have like an optimization problem on this manifold? And this is very important in physics. It's like a holy grail of physics. Like, so you're given with a function on these manifolds and you want to minimize it, okay? And there we propose like a different algorithm that like that's a problem people are approaching like already for like I know, like 50 years. And I think we managed to like convey some like fresh thoughts by introducing these kind of tools from differential geometry on manifolds for this fundamental problem of quantum mechanics. And if you are interested in this stuff, in this picture, I would say, then you should definitely give it a read. Yeah.
Okay, if you're as excited as I am about these follow-up works that Kirill talked about, then well, don't forget to come to the future reading group sessions, and you can also sign up for our email mailing list or for Slack. Everything in the description to be updated about when we'll be talking about these works.